So thank you very much. Very nice presentation, Paulo. Thanks a lot. We may continue discussing on the Slack channel. So hi everybody, was an honor to get this best paper. We are very happy to hear of it, and I hope you enjoy also the presentation. I try to do my best to be on time. So this is a collaboration with some friends from my university, PUC Rio, Catholic University, and some also friends from the Fiocruz, which is Biological Institute in Rio too. And this is basically part of a former PhD candidate, Cristian, who defended a few years ago, and then we are publishing the complete thing only a few years after. Anyway, so the idea is to argue about why not using relational text types to represent biological sequences. It's a very simple problem, and let's see if I can explain to you the main ideas. Well, first of all, just to give you an idea of kind of things we are working on biological databases area. So it's been for a long time we are working on biological issues and mainly database-oriented approaches. So we are working on device drivers for BLAST, and we are working on some way to improve the memory management during this execution of programs that we are used to, everybody knows and everybody uses. And we also have presented some works in previous years on integration on databases and data sets from biological informations. Also distributing and parallel issues on BLAST again and some other programs, database fragmentations and workflows. So we've been working many issues on biological applications and always with a database point of view. So the main question, the main research question here is, we have a kind of a how we say, very large, not very large database, but very large sequences. So usually you have this large string that represents the data we need to represent in our research. And there's always a question, what do we do with this large strings, very large sequences, and how do we represent, model, and store, and process, and the way we do. So many people still work with text files. These are still present. Many people are considering like, okay, I will keep the original files from whatever data set they have collected it. And people mostly they run scripts on many languages, like recently more Python stuff, but there are Perl things and Lua too, and you can run scripts special oriented to deal with this kind of strings. But why not think about something like using a data type, existing data types in some database management system like text, varchar, and blobs, and there are functions already existing that you could use. The only problem here is that these functions, they don't have anything to do with the biological domain. So they are just functions on strings, but there are no semantics. So the thing is, why should we keep on doing this? And why not use all the existing advances on relational databases and all other database systems we know, and try to represent it in a better way? So we have a claim. A claim is, okay, we can represent this data as strings and blobs, as many people do. It's an easy way to do it, but there are no semantics. So what could we do as a simple way? So is think about to extend some idea of representation and build up some functions and represent the semantics in such a way that we can not deal with only strings, but some kind of biostrings as a new data types. And it's important to note that not only we have a problem, an open problem still about representing in abstractions, like the modeling way, but also in persistency. So it's a tough way to represent this very large sequence. It's still a tough job to do it, and we still have a lot of work to do about it. So the alternatives in our situation was, well, we can build something from scratch and do some modeling and do all the implementation. This could be very optimized in the way we were looking for to resolve some problem we were looking for before. But this is very tough to do. So the idea here was to do some extension. So use something that exists, like the text types. And this is not the best part to do, considering abstractions from the real world. But I think this is at least much easier to do in a more straightforward way. The inspiring idea comes from some already existing extensions for temporal databases and geographic databases. For example, we have some special types like the date and type types that you give some kind of representation and a precise persistent view. And then you have functions that you can write specifically for this kind of types. So in our case, our proposal is a basic proposal inspired on the text types from the relational database systems. In our case, we have implemented and tested it on the PostgreSQL DBMS. We have worked with some biological projects that the people come to us and they say, we need this function and this other function and this other process. Could you please make it already available for us? So people that are not specialists, they may access all this content and work as if they don't need to understand how things are actually implemented. So some of these functions were the reverse functions, the get GC, the GC biased content that may lead to some information about proteins, the transcripts, the translations, searching for ORFs that may lead to proteins too. So these are all functions that people are always asking us to do, like scripts. And we have decided to do, why not to write functions and try to adopt all these text types with some semantics related to the biological domain. And the persistency comes for free for all the DBMS that you have that already deals okay with all these text types. So some useful functions, we have some more that we have already implemented, but at that time we had a specific experiment that we were looking forward to finish with our colleagues. So one of the functions were the complement sequence. We give a sequence, we give its complement, but there's a biological semantics in this case. So it's not just a simple pattern matching. It's something that deals actually with the biological experiment we're dealing with. The reverse sequencing that may, sometimes we adopt the 5' 3' way of looking at the sequences, but you can sometimes take a look in reverse way. So it's useful to have the reverse. As we said before, the idea of people are keeping an eye on the way of, if you have a sequence and if you want to take a look of something that may be important for your research, and that you get out of the random way of checking all the sequence formation. And then one of the things people do in practice is to look for the GC biased content, and then you can have some pointing to some important relevant questions on biological content. Some others are the transcript and the translation related to the central dogma of biology. So it's they are kind of straightforward functions too, but some of them they need some extra information. Some, for example, the translation function relates to some external table that you need to implement and take a look to do all the combinations and refer to the translation from a sequence to the corresponding protein. And then also the idea of searching ORFs that makes the things easier for biological people when they know how to program. They don't want to know, and they don't want to know about the implementation details. So you offer them some of these functions so they can use it directly and from a nice and user interface. Anyway, so at that time, we were looking at a specific case study. Was dealing with similarity management. We had about 1 terabyte of sequences like these ones you have on top of your screen. Many information involved. We had to do many comparisons and many findings that we were asked about it. We had already the problem of representing it and storing it, and then afterwards to offer some kind of interface so people could ask some relevant questions like these ones I put in for you, but there are many more. So I want to know what are the proteins that comes from original genomic sequences. People asking also questions about the taxonomic groups, how many genomes and proteins you get from kind of some lineage that you can look through from some species. When you look for some programs, specific programs too, that give you some hits for data you are looking for. So how many hits you get from this kind of data set you're using at that time. Some other questions that are more philosophical ones, like are there unique genes or something related to some species that you're looking that maybe these genes are present only there, so you may infer some properties of those species, and then you can maybe evaluate in a different way when compared to other species you are looking for in your particular research. So our goal was what many people are seeing many other works that claim that a more conceptual view of the biological domain should be carried out, not to inform technological stuff, but maybe to represent the most we can things we learn from the domain, and then we can learn a little bit more how we can represent those text types, and finally, eventually, we'll get to the constructions of the functions we needed to build. So the idea here was to first consider some existing relationships, like the gene ontology, always present ontology that many people use, some taxonomies to guarantee those lineage that we were talking before, and the idea of checking for paralogs and orthologs that I mentioned also in the questions. We have all the hits that make, we know that proteins always come from ORFs, but not all ORFs are leading to proteins. So we may ask what happened when you look in details about all this data, and you can check for other possible proteins for all the sequences you have before. So the idea here was to have an abstract model, the more conceptual one related to the biological domain. And we don't have time to do it, but you know, we can proceed with some relational and other models too, for logical models to get a database, an actual database. And then our approach was to do this conceptual schema to have as input all the domain queries people were looking for. We prepare some analysis checking if all the data, the available data is there. And then we do the validation with the translation from the conceptual schema to the logical schema. And we did the implementation of some of the functions I've mentioned before. And like these others that, you know, I want to get a taxonomy ID. I want to count proteins and some hits and taxonomies. And I want to do some translations and transcripts and searching for ORF. So things get much more easy for people, for final users to end users to check for the information they need. I didn't want to, in our paper, we have all the details for the implementations. I'm just showing you the idea of some simple functions. There are some other functions that are a bit more complicated, but this one I wanted to show not because this one is very simple, but also because sometimes we can use functions that exist already for general strings, like replace function. So we can use some function that was built for any string manipulation, but in this case we used to get GC content with this GC biased information. So just to end up and do a quick presentation and maybe have some time for answering questions. The question here is, relational model is still alive. Many people are trying to kill it, but it's a very interesting the database model. Database systems are still okay. Biostrings are okay too. We think we can work around many problems, and the lack of semantics we can add up with some functions and maybe try to look further into actually ADTS. And for those that want to try out, what we have done is there's the address for the GitHub. And you can download the particular implementation of Postgres. And if you can take a look at all the implementations, all the functions, and I'm ready. I'm here for answering any questions you want. So, obrigado, thank you, grazie, danke.
Thank you very much, Sergio. Very nice presentation. We liked very much your paper because it connected conceptual models with actual implementation problems. Here we have a question from Stefano. He's asking, do you also provide special physical optimization for the typical biological queries function in PLPQSQL, like indexing? And do you hit performance problems so far?
Yeah, well, that's a good question. As I mentioned before, hi, Stefano. And nice to see you too. We have worked at the high level before. So the abstractions are, we have worked on the abstractions before, and we are using all the stuff that Postgres or any other relational system could offer you. So we're not working on the physical structures and the physical implementation so far. There's another student of mine that have worked a little bit on this, but in this presentation, in this work, we had focused mostly on the idea of the abstract data types.
So we have another one quick from Oscar. I'm really sorry, we're a little bit behind, so we're gonna have to make a very brief break, but this is kind of interesting. So we go ahead with it. Oscar is asking, have you had any initial proposal, including a precise set of proposed function I like very much your idea of a new specific data type. So congratulations. The question is, oh, sorry, this was kind of repeated. Have you had any initial proposal including a precise set of proposed functions? So different types of sequences. So you're considering DNA, RNA, proteins. And I would like to add something myself. I noticed from the paper that you were considering mostly coding regions, while in the last years, non-coding regions are becoming more popular and interesting. So have you considered extending the approach to this?
Well, actually, the approach is, the first thing is, thank you, Oscar, and thank you, Anna, for the questions. The approach is to consider these text types as the basis for the representation, but all the semantics for DNA or RNA and everything else, as CDS and ORFs, all the semantics comes with the function. So what we have seen is we've practiced a lot, and this seemed a very good way to do it, because if you offer to the end user only these abstractions coming out from the output from the functions, they don't see the precise implementation on the text types. And so you can work on, specifically if you want to work on DNA or RNAs or proteins, you have all these functions that show you exactly where you can work precisely. And then you can build up many other functions using these existing functions too. So the idea here is it's to open up for a second step of abstractions instead of working on the text type. So I know we don't have many time to continue. We can keep on up on discussions on the Slack channel. But,
yes, please. I invite you to do it also because Oscar had more questions.
Yeah,
so
I see. Thank you very much for the questions. But okay, we don't have time. I will try to answer all this on the Slack channel.